Hi, I am Jay Prakash, lecturer from Computer Science and Engineering Department, Government Polytechnic for Women, Bengaluru. So today we start the first session on Unit 2, which is Machine Instruction and Programs. The memory consists of many millions of storage cells. So each cell stores one bit of information. The value may be either 0 or it may be 1. So these storage cells are also called as flip-flops. Each group of n bits is referred to as word of information, and n is called word length. So a group of n bits is called as word, and, and n is called as word length. The word length can vary from 8 bit to 64 bits. The unit of 8 bits is called as bytes. So a number of 8 bits is called as 1 byte. Accessing the memory to store or retrieve a single item of information requires distinct address for each item location. So in order to find out the any item or any location, we need a address. So address refers to the location of the particular data. It is customary to use the numbers from 0 to 2k minus 1 as the address of successive locations in the memory. If 2k is equal to the number of addressable locations, the 2k addresses constitute the address space of the number. So initially starts from 0, so at the end will be 2k minus 1. The objectives. The machine instructions in the program execution including branching and subroutine, call and return operation. So for executions, we need a different operations like branching. So going from one step to the other step, or subroutine call or return operations. The number representation and addition subtraction in the two's complement systems. So we are going to represent the numbers in the form of binary numbers in the computers. Addressing method for accessing registry and memory operands, and assembly language used for machine instruction because the machine cannot understand the human readable language. So it has to be converted into machine readable language. So assembly language can be used. The program controlled input output operations can be used. So before going to the instructions, we find out what is number, arithmetic operations, and characters. So in a computer, we represent the number by in the form of binary. There are signed integers. There are three major representation: sign and magnitude, one's complement, two's complement. And the assumptions that there is a 4-bit machine word and 16-bit different values can be represented. So signed and magnitude representation. Here the value 0 represents that the number is positive and the value 1 represents that the number is negative. So one's complement representations. In the case of one's complement representations, what happens here is whatever the number we have, so we are going to complement. So it is a reverse. Either if it is 0, we are going to make 0 as 1. If it is 1, we make it as 0. So this is called as one's complement representation. So in the case of two's complement representation, it is first we do the step of one's complement representation and add 1 to the element whatever we got, then we get the two's complement representation. So here, whatever the number we have to do the first one complement, then add number 1, then it represents the two's complement representation. So these are the binary sign integer representation examples. So let us start with memory locations, address, and operations. So memory location. So in order to find out the cell or the data, we need an address. Okay. So how the memory exists? Memory is the storage location where with the data has been stored. The memory consists of many millions of storage cells. So each cell stores one bit of information, either 0 or 1. Data is usually accessed in n-bit groups. N is called word length. So this is called n bits. So this is the first word. This is the second word. So successively it will move to the last word. So in this order, the successive order, the numbers are going to be get stored, or the bit of information are going to be get stored. So the data is usually accessed in n bits. So for example, a 32-bit word length example. Okay. So B0 to B31. So initially starts with 0. So it will ends in 31. So this is a 32-bit word, 32-bit length. Okay. Next, the B31 is equal to 0 for positive numbers. So the last box, that is nothing but this. So here, if the value is 0, then the number is represented as positive numbers. If the value is 1, the number is represented as negative numbers. Okay. So if you divide the 32 bits into 4 blocks, okay, in 4 blocks, So 32 divided by 4, it will happen to the 8 bits. So one block occurs 8 bits. So there are 4 8 bits. So 4 into 8. So 32-bit words is, this is the word length. The memory locations. Okay, to retrieve the information from the memory, either from one word or one byte, addresses for each locations are needed. For example, a k bit address memory has 2 to the power of k memory locations. So for k bit, it represents the exponential of 2. That is, the 2 to the power of k memory locations will be there. We can access the data from that. For example, for a 24-bit memory, 2 to the power of 24, so 16,777 memory locations will be there. For a 32-bit, 2 to the power of 32. So for 1 kilo, kilo means 10. So 2 to the power of 10. For tera, 2 to the power of 40 memory locations will be there. The memory location, addresses and operations. It is impractical to assign distinct address to individual bit locations in the memory. So for each bit, we cannot reference the address. So for that, the most practical assignment is to have successive address refers to successive byte. So successive address as refers to the successive byte locations in the memory, byte addressable memory. The byte locations have the address either 0, 1 or 2. If the word length is 32 bits, then the successive are located under the address 0, 4, 8. So each word having 4 bytes. So next one is the big endian and little endian assignments. So what happens in the case of big endian? Here the lower byte address are used for MS, most significant bytes of the word. That is the MSB of the word. So in the big endian, the lower byte addresses are used for MSBs, whereas in the little endian, it is an opposite. So the lower byte addresses are used for LSB. That is the least significant byte. So this is the diagram where represents the big endian and the little endian. Next, the addressing ordering of the bytes. The word alignment. The words are said to be aligned in the memory if they are begin at the byte address. That is the multiple of number of bytes in the word. For example, a 16-bit word. So the word address will be 0, 2, 4. If it is 32 bits, so 0, 4, 8. If it is a 64-bit word, then the word address will be 0, 8, 16. Accessing the numbers, characters, and the character strings. Okay, what happens? A number usually occupies one word. It can be accessed in the memory by specifying its word address. So word can be referred by the word address. Similarly, individual characters can be accessed by their byte address. So the bytes can be accessed by the byte address and the word is referred by word address. There are two ways to indicate the length of the string. A special control character with a meaning end of the string can be used as the last character in the string. Okay. A separate memory word location or registers can contain a number indicating that the length of the string in the byte. So character, a group of word or group of character reference as string. So this is the MCQ questions. Each cell can store dash amount of information. So obviously what is the answer? Each cell can store one bit of information, either 0 or 1. Next, each group of n bits is called referred as word. Okay. Next, a unit of 8 bits is called as dash. So byte. So 8 bits referred as 1 byte. Next, in the big endian, the lower byte address are used for MSB of the word. Dash of the word, MSB means more significant bytes of the word. Whereas in the little endian, the lower byte address are used for dash of the word, LSB. Okay, least significant bytes of the word. So this ends the first session of the unit 2. Thank you.